You could fit the entire city of San Francisco inside this hole in the ground, and there would still be room left over. The Bingham Canyon Mine in Utah isn't just the largest open pit mine in the world. It's a man-made canyon so vast that it generates its own localized weather patterns, complete with unique wind currents, temperature variations, and even occasional snow that falls only within the pit while the surrounding desert remains dry. This single excavation represents the pinnacle of humanity's ability to move Earth on an industrial scale. Every year, Bingham Canyon produces over 300,000 tons of copper, along with significant quantities of gold, silver, and molybdenum. The mine has generated over $20 billion in metals since operations began in 1906, making it one of the most valuable holes ever dug. For over 12,000 people work directly or indirectly to keep this operation running 24 hours a day, 365 days a year. The copper extracted here supplies roughly 2% of global demand, finding its way into everything from electrical wiring to smartphone components to renewable energy infrastructure. Without mines like Bingham Canyon, the modern electrical grid simply couldn't exist. The process starts with what mining engineers call overburden removal, stripping away everything that isn't valuable ore. Massive hydraulic excavators, each weighing over 800 tons and standing 4 stories tall, tear into the mountainside with buckets that can hold 40 cubic yards of material. That's enough to fill a standard garbage truck in a single scoop. The sound is overwhelming. A constant grinding roar of diesel engines, hydraulic systems, and rock being crushed and moved. And these machines operate in temperatures that can swing from minus 20 degrees Fahrenheit in winter to over 100 degrees in summer, all while working at an altitude of over 6,000 feet above sea level. Each excavator can move up to 4,000 tons of material per hour, working in carefully choreographed patterns that prevent the pit walls from becoming unstable. The operators, sitting in climate-controlled cabs suspended 40 feet above the ground, and use GPS guidance systems to ensure they're digging in exactly the right location. A single mistake could destabilize millions of tons of rock above. The overburden, mostly worthless rock and soil, gets loaded onto haul trucks that are themselves engineering marvels. The haul trucks that move material out of Bingham Canyon are not trucks in any conventional sense. Each Caterpillar 797 weighs over 1,400,000 pounds when fully loaded and stands 24 feet tall. Their tires alone cost $42,000 each and weigh over 11,000 pounds. When one of these trucks drives past, you feel the vibration in your chest from hundreds of yards away. These mechanical giants burn roughly 1 gallon of diesel fuel every 2 minutes while operating. But they're essential because they can carry payloads of up to 400 tons, equivalent to the weight of about 200 cars. The trucks follow predetermined routes carved into the pit walls, climbing grades that would challenge a mountain goat while carrying loads that would crush highway bridges. Each truck represents a $4 million investment and requires a team of specialized mechanics to maintain. On any given day, over 100 of these trucks are moving through the mine, creating a constant parade of industrial power that never stops. When the overburden is cleared, the real mining begins with controlled explosions that would make military demolition experts envious. Mining engineers drill precise patterns of holes into the rock face, each hole exactly 40 feet deep and spaced according to computer calculations that account for rock density, fracture patterns, and the desired size of the resulting fragments. The drilling rigs themselves are massive, tracked vehicles with masts that extend over 60 feet into the air, capable of drilling through the hardest granite with diamond-tipped bits. The explosives used aren't dynamite, but a sophisticated mixture of ammonium nitrate and diesel fuel called ANFO, combined with specialized boosters and timing devices. A single blast might use over 100,000 pounds of explosives, detonated in a sequence timed to the millisecond. The explosion creates a seismic event that registers on earthquake monitoring equipment hundreds of miles away. But the real artistry is in controlling the blast, so that the rock breaks into pieces small enough for the excavators to handle efficiently. Too small, and you waste energy. Too large, and you can't move the material. Once the copper-bearing ore is extracted, it begins a journey through one of the most sophisticated mineral processing facilities on Earth. The ore gets fed into primary crushers, machines the size of small buildings that can reduce boulders weighing several tons into fragments no larger than 8 inches across. The crushing force involved is almost incomprehensible. Over 4,000 tons of pressure applied through massive steel jaws that open and close like a mechanical dinosaur. From the primary crushers, the ore moves to secondary and tertiary crushing stages, each one reducing the particle size further while separating valuable minerals from waste rock. The entire crushing circuit processes over 150,000 tons of ore every day, operating with the precision of a Swiss watch, despite handling material that would destroy most industrial equipment in minutes. The noise level inside the crushing facility exceeds 120 decibels, loud enough to cause permanent hearing damage in seconds without protection. The crushed ore then enters the concentration process, where it's mixed with water and chemicals in massive flotation cells that look like industrial hot tubs. Air bubbles are injected into the mixture, and through a process that seems almost like magic, the copper minerals attach to the bubbles and float to the surface while the waste rock sinks. This process recovers over 90% of the copper from ore that contains less than 1% copper by weight. It's an extraction efficiency that would have seemed impossible to earlier generations of miners. The copper concentrate from the flotation process still contains only about 28% copper, mixed with sulfur, iron, and other elements. To extract pure copper requires smelting, heating the concentrate to over 2,000 degrees Fahrenheit in furnaces that consume enough natural gas to heat a small city. The smelting process takes place in a facility where the air shimmers with heat waves and the floor vibrates from the power of industrial furnaces that never cool down. Inside the smelters, the concentrate melts into a molten mixture called matte, which is then processed further in converters that blow oxygen through the liquid metal at supersonic speeds. The chemical reactions involved release enough heat to melt steel, and the entire process produces copper that is 99.9% pure. The byproducts aren't waste. Sulfur dioxide gets captured and converted into sulfuric acid, which sells for millions of dollars annually. Even the slag, the rocky waste from smelting, gets processed to recover additional metals and then sold as construction material. Modern mining operations like Bingham Canyon incorporate environmental management systems that would have been unimaginable decades ago. Water used in the processing circuits gets recycled through treatment plants that remove heavy metals and adjust pH levels before the water returns to the process. Over 95% of processed water gets reused, reducing fresh water consumption to a fraction of what older mining operations required. Air quality monitoring stations positioned around the mine track particulate matter, sulfur dioxide, and other emissions in real time, with data transmitted to regulatory agencies continuously. When weather conditions might cause air quality issues, operations can be modified or temporarily suspended. The mine even employs full-time wildlife biologists who manage habitat restoration projects and monitor the health of local ecosystems. Waste rock from the mining operation doesn't just get piled randomly. It's engineered into stable landforms that will remain stable for centuries. Some waste rock piles are over 600 feet tall, constructed with internal drainage systems, and covered with specially selected soil and vegetation that can thrive in the harsh mountain environment. These aren't just dumps. They're engineered landscapes designed to blend back into the natural environment over time. After months of processing, the copper that began as barely visible flecks in mountain rock emerges as 99.9% pure cathodes. Sheets of metal so pure they conduct electricity with almost no resistance. Each cathode weighs about 225 pounds and represents the culmination of a process that moved literally tons of earth. These cathodes get shipped to manufacturers around the world, where they become the copper wire that carries electricity through your home, the components in your smartphone that enable wireless communication, and the motors in electric vehicles that represent the future of transportation. The scale of transformation is staggering. To produce a single ton of copper requires processing approximately 300 tons of ore and moving over 1,000 tons of overburden. Yet this ratio makes economic sense because copper is so essential to modern technology that global civilization would grind to a halt without it. Every electric motor, every circuit board, every power transmission line depends on copper's unique combination of electrical conductivity, corrosion resistance, and mechanical strength. Standing at the edge of Bingham Canyon, looking down into a hole that extends over half a mile into the earth and spans nearly 3 miles across, you're witnessing more than just mining. You're seeing humanity's ability to reshape the planet itself in service of technological progress. The copper extracted from this single location has enabled countless innovations, from the electrical grid that powers cities to the renewable energy systems that may help save the climate. Every time you flip a light switch, charge your phone, or drive a car with electronic systems, you're using copper that may have come from this extraordinary excavation in the Utah mountains. How many other hidden industrial processes shape your daily life in ways you never consider? And what would happen if they suddenly stopped? If this glimpse into industrial-scale mining fascinated you, subscribe for more deep dives into the massive processes that power our modern world.